Welcome to DC Digital Learning Session. Today we have to discuss interpolation with equal intervals. Under this, already in earlier classes, we know the Newton's Gregory forward interpolation formula. Now I have to discuss Newton's Gregory backward interpolation formula. Already we know the introduction. Here, let y0, y1, y2 and so on, yn with the values of an unknown function y is equal to f of x corresponding to equidistance values of x0 plus h, x0 plus 2h and so on. Suppose that it is required to evaluate f of x for x is equal to xn plus ph. That means the estimate the value of y at end of the interval or nearer to end of the interval where p is any real number. In this case, we can use Newton-Gregory backward interpolation formula. Now we define E such that e raised to p f of x is equal to f of x plus ph. Therefore, it is denoted by yp. Yp is equal to f of xn plus ph. That is equal to e raised to p f of xn. That is equal to, now using the relation between e and nabla, e is equal to 1 minus nabla whole to the power minus 1. Here instead of e, we put 1 minus nabla whole to the power minus 1 whole raised to p. It becomes 1 minus nabla whole to the power minus p into yn. And expanding 1 minus nabla whole to the power minus p by using binomial expansion and simplify, we get yp is equal to yn plus p into nabla yn plus p into p plus 1 divided by 2 factorial into nabla square yn plus p into p plus 1 into p plus 2 divided by 3 factorial nabla 3yn plus and so on, which is called Newton's Gregory backward interpolation formula. We note that to estimate the value of y at a desired value of x near the end of the table or the end of the intervals, okay, at that time only we can use Newton's Gregory backward interpolation formula. Newton-Gregory backward interpolation formula is also called Newton backward interpolation formula. Now we have to discuss some examples. Find the value of y at x equal to 7.5 from the given data. Here x equal to 7.5, it lies end of the interval. It is very close to 8. Therefore, here we have to use Newton's backward interpolation formula. Okay, here data is given x and y's. Now, first construct backward difference table. Because the value of x nearer to end of the interval. Therefore, we construct backward difference table. Here, this is the backward difference table, x and y's. Here, nabla yn. This is a nabla yn. This is nabla 2yn, nabla 3yn, nabla 4yn. Here, x0, x1, x2, x3, x4, x5, x6, x7. Here, y0, y1, y2, y3, y4, y5, y6, y7. Therefore, this is a nabla y7, nabla square y7, nabla 3y7, nabla 4y7. These are the backward leading differences. This is y7, this is x7. Now using the formula, here from the table, here x7, here we have to take xn. xn is 8, xn is 8 and x is 7.5. You have to estimate y at x equal to 7.5 and h is the step length, h is equal to 1 and y7 here we take yn is equal to 512. Therefore, x is equal to xn plus ph. This implies p is equal to x minus xn divided by h. X minus xn divided by h. In forward interpolation, we take x equal to x0 plus ph. This is a backward interpolation. Therefore, we have to take x is equal to xn plus ph implies p is equal to x minus xn by h. Therefore, here x equal to 7.5. Xn is the last value. This is xn is 8 divided by h. H is 1. After simplification, p is equal to minus 0.5. Now from the table, note down delta y, nabla yn, nabla 2 yn, nabla 3 yn, and nabla 4 yn, and so on. This is a nabla 4 yn. Nabla 4 yn is 0. Nabla 4 yn. This is actually not nabla 3, nabla 4 yn. Nabla 4 yn. Nabla 4 yn. This is 0 from the table. Now using backward interpolation table, f of x is equal to yn plus p into nabla yn plus p into p plus 1 by 2 factorial nabla square yn plus and so on. Here we know that all the values from the table and from the given data substitute in the formula and simplify, we get f of 7.5 is equal to 421.87. And another example, the following table gives the values of tan x for x lies between 0.1 to 0.3. Find the value of tan of 0.26. Tan of 0.26. Here 0.26 is near to end of the interval. Therefore, we can use backward interpolation formula. Here, construct a backward difference table. Here x and y. Here nabla, first backward difference, second backward difference, third backward difference, fourth backward difference. Here x0, x1, x2, x3, x4, y0, y1, y2, y3, y4. This is a nabla y4, nabla 2 y4, nabla 3 y4, nabla 4 y4. And you can note down all the values: xn, yn, nabla yn, nabla 2 yn, nabla 3 yn, nabla 4 yn. Here using the backward interpolation table, substitute all the values at x is equal to 0.26. We get 0.26602. Tan of 0.26 is equal to 0.26602. This is the required value of f of x. And another one, find the cubic polynomial which takes the following values and hence evaluate f of 4. Here f4, it lies outside the interval, but it is very close to 3, end of the interval. Here we find the interpolating polynomial by Newton's backward interpolation formula. First, construct backward difference table. Here x are given, x is equal to 0, 1, 2, 3, and y is equal to 1, 2, 1, 10. And these are the leading differences, backward leading differences. Now, from the data, xn equal to 3, h equal to 1, yn is equal to 10. Now x equal to xn plus ph, this implies p is equal to x minus xn by h, that is equal to x minus 3 by 1 is equal to x minus 3. Here p is equal to x minus 3. Now from the table, delta yn is 9, delta 2 yn is 10, delta 3 yn is 12. Now by backward interpolation formula, f of x equal to yn plus p, nabla yn plus p, p plus 1 by 2 factorial, nabla 2 yn plus p into p plus 1, p plus 2 divided by 3 factorial, nabla 3 yn. And we know that all the values substitute and simplify, we get polynomial in x. F of x equal to 2x cube minus 7x square plus 6x plus 1. Here, take x is equal to 4, we get f of 4. F of 4 is equal to 41. And one more example, the population of a town is as follows. In the year 1921, 20 lakhs. In the year 1931, 24 lakhs. In the year 1941, 29 lakhs. 1951, 36 lakhs. 1961, 46 lakhs. 1971, 51 lakhs. Estimate the increase in population during the period 1955 to 1961. Here, how much population increase between 1955 to 1961? Here, the year 1955 and 1961 are very close to end of the interval. Therefore, here we have to use Newton's backward interpolation formula. First, construct the difference table, backward difference table. Here X are 1921, 1931, 1941, 1951, 1961, 1971, and given values of Y, corresponding population 20 lakhs, 24 lakhs, 29 lakhs, and so on 51 lakhs. Now backward differences 24 minus 24 like this. You can write all the backward differences. Here this is YXN, YN, nabla YN, nabla 2YN, nabla 3YN, nabla 4YN, nabla 5YN. Now x equal to xn plus ph. This implies p equal to x minus xn by h. X is 1955, xn is 1971 divided by h. H equal to 10 here. Therefore, p equal to minus 1.6. Now, from the table, these we know from the table and backward interpolation formula. We can write down the backward interpolation formula and substitute all the values. Simplify. We get the population at 1955 is 39.983 lakhs. The increase in population during the period 1955 to 1961 is equal to 46 minus 39,983 is equal to 6.017 lakhs. Here the population increases here to here. Here at 1961 is already we know the population 46 lakhs. At 1955 is 39.983 lakhs. Take the difference, we get increase of the population. The increase of the population during the period here 6.017 lakhs. This is the required answer. And similarly, we can estimate here another problem. Here given sine 45 degrees given, sine 50 degrees given, sine 55 degrees given, sine 60 degrees given, find sine 57 degree. Here 57 degree is the end of the interval. Therefore, here also we can use Newton backward formula. We get the answer. Okay. Now we can estimate, and these are the another problems. Can go through the problems, and those are interested, you can go through these problems. You can try to solve these problems, and these are the references. You can try. Okay. Thank you.